Hello, you beautiful people. So today it's time again for chemical reaction engineering. And last time you got a homework about reaction in parallel, taken from the book from Octave Levenspiel. And today I want to tell you how my solution, what it looks like. So what you had is you have two reactions. A and B can form C, which is the wanted product, or A and B can form an unwanted side product D. And I gave you the following reaction rate. So for reaction 1, we had the exponent of the concentration of component A was 1.5, and the exponent for concentration B was 0.3. And for reaction 2, so the unwanted reaction, the coefficients or the exponents were 0.5 and 1.8. Okay, and yes, if you say, okay, this is my component C that I want to have, so for which I get the money, then it's quite easy to see that you have to somehow make sure that the reaction rate 1 is higher than the reaction rate 2. And yeah, how can you find out what to do? A simple solution is that you just take the ratio of these two reaction rates, that you just say R1 over R2, and then you see here the K, both have the value of 1, so this equals out. 1 over R equals out, and then you have left over here this kilomole per cubic meter to the power of 0.5. Looks a bit weird, but this is just if you divide this by each other. And then you have the Ca, you have 1.5 and 0.5, so here you have the exponent 1, and here you have 0.3, and on the lower side of your fraction you have 1.8. So you end up with 1.5. So you can write it, your ratio of your reaction rate is this weird units fraction, and then you have Ca over Cb to the power of 1.5. And if you want to make sure that your R1 is bigger than R2, then you can find out that you have to make sure that Ca is quite high and Cb should be quite low. Okay, this is what we had in mind. And then I gave you 3 setups which you should simulate. And the setup 1 was you start with a high amount of component B and you continuously feed your component A to this reactor. So semi-batch operation, you know this already, and for this you can just use your MATLAB code where we use the Euler scheme, and then you can simulate it. If again we look at this, so with the first setup you have a continuous feed of component A, so this means you have a rather low concentration over a long period of time, and you start with a high amount of component B. And so if you look here at the ratio, then you will find out that this should be kind of a bad solution. Let's have a look at the plot. Here you can see our reaction time. Again, it's 6 hours. We have a continuous feed over 5 hours, and then just 1 hour of batch reaction. And the red thick line is our wanted component C. And you can see that this looks quite poor. You only get a concentration of 0.31 kilomole per cubic meter, and you have really a lot of component D. So this is not such a good solution to the given task. And here again you can see what is our concentration of component B. It starts with a high amount and it decreases continuously, and component A, you just have a very low concentration because everything you feed to your reactor is immediately consumed. Unfortunately, it's consumed by reaction 2, so not a very good solution. Then let's have a look at the setup 2. Setup 2 was you start with a high concentration of component A and you feed B continuously to the reactor, so it's just the other way around, it's vice versa. And from what we found out so far, you should expect that this should be kind of a good solution. And if you look at this, you can see that your component C now really, you produce it a lot, 1.91. So it's really dominating the reaction. Your component D is really low. It's about 1.0, I would say. And here you can see A. You start with a high concentration. B, it's almost here in the beginning. You almost have no measurable concentration of your component B, so it's very good for this kind of reaction. And setup 3 was a pure batch reaction. You start with both as a high amount, and then your reaction look like this. So you have nearly the same amount of component C and D. So from if you want to optimize your reaction, it's also not such a good idea. So from my point of view, if you just have these 3 setups, then the best thing is to choose setup 2, where you continuously feed component B to your reactor. To make it a little bit more clear, I put here some plots of the reaction rates. So this is setup 1, setup 2 and setup 3. So I don't want it to waste 3 more slides, so I put it all in one. Hopefully this is big enough for you. So setup 1, you can see reaction rate 2 really dominates the reaction. It's really high. Reaction rate 1, it's only increasing a little bit at the end. If you go for setup 2, so this is the good one, here you can see that this is what we want. We want a high value for reaction rate 1 and very low for reaction rate 2. And for the batch operation, setup 3, you can see that you start very fast at the beginning and then it's decreasing and decreasing and decreasing. Okay, so here you can see a strong difference in the reaction rates, because what I told you so far, you have to make sure that this is high, this is low, and I think if you look at the concentration profiles or the reaction rate, it's quite obvious that setup 2 is good. Maybe one more comment. If you say, okay, maybe this is I don't want to go for a semi-batch reaction, but I want to keep batch operation, because then I don't have to take into account that my volume is increasing and I don't have to install a pump or whatsoever. If you want to stick to the batch operation, what you can just easily do is that you increase your starting concentration or your starting amount of moles of component A. So again, what is important for this reaction is that you have a high amount or high concentration of component A, and you can do this by increasing the moles at the beginning. So here I did this for a few values. So what I gave you in your homework was 20 kilomoles. Oh, this shouldn't be kilomoles per cubic meter, this should only be kilomoles. Sorry about that. If you increase this to 22, then you can see, okay, my component C, the concentration of component C is increasing, and if I increase it further to 24, then I even increase it further, and 26, here I stop the simulation. You can see, okay, it goes like 1.4, and the concentration of the unwanted component D is decreasing. And positive side effect is that your reaction is nearly finished after 1.5 hours. So if you don't go for semi-batch operation, but if you go for an increased amount of moles at the beginning, then you can also have an effect on your concentrations, and you can significantly reduce your reaction time. If you want to try this on your own, then you have to make sure in your MATLAB model that you somehow include an if condition, because due to this reaction kinetics that we produce with this weird exponents, you can easily get negative concentrations, and this doesn't make sense. So nature doesn't know negative concentrations, but mathematics can easily calculate negative concentrations. So yes, you just have to make sure that you have something like an if condition. I will upload my MATLAB code to the email room, and then you can have a look. Yes, okay. So what was your homework? Your homework was simulate the concentration profiles for the 3 setups. So here we can make a check. Choose the best option for this reaction type. Justify your choice. Whoops. No. We also did this just by looking at the results, and we also had a look at the what's wrong here. Holy moly. We also had a look at the reaction rates. We just did this by R1 over R2. And yes, and then the next the last question was, so what we found here for batch or semi-batch reaction, is this also possible for the continuous stir tank reactor, for the plug flow reactor of our tank in series? And if it's possible, how would it look like? How can you make sure that you have something like a feeding to your tank in series or whatsoever? Okay, let's start with the continuously stir tank reactor. So what is very typical for the CSTR is the homogeneous concentration inside the CSTR, because we have a perfect mixing and very intensive stirring. So it doesn't matter where you are here, you always have the same concentration inside the vessel, and this is always the same as the outlet concentration. So it doesn't make a difference if you add your main flow here with component A and then you have a side entry with component B. Everything is mixed perfectly well, and so here you can't take any advantage of this, of our no knowledge. So a staged feeding of our component B is not an option, and if you want to do an reaction like we have here in our example, if you want to do it, then you just can play around with the starting amount of moles, so Na0, and this is your only choice to manipulate the value of Cc. So here for the CSTR it's not working. Let's have a look at the plug flow reactor. So for the plug flow reactor you have just like a big tube here, and let's assume you start here with the inlet concentration Ca0, and what you can do quite easily is just that you drill some holes along your plug flow reactor, and then you can have here some additional feeding points to your plug flow reactor. So here you would add your component B along the plug flow reactor, and with this you can make sure that your concentration of B is kept at a low value along the plug flow reactor. So for plug flow reactor this is working, so this can be done. If you want to simulate this, then you have to take into account that since you are adding your component B all along the PFR, you have to make sure that your volume flow also increases, and this means you have a higher velocity here at the end compared to the beginning. So here you can see the velocity arrows are a little bit bigger than here at the beginning. So if you want to simulate this, then you have to make sure that here your residence time in this section of the PFR is shorter than your residence time in this section of the PFR. But basically it's working. Okay, tank in series. How does it look like? So I think you know this. You start here, you feed it to the first reactor, then to the second, and so on. And yes, what you can do here is you can you split up again your component B. You add a little bit of B here, a little bit of B here, and then also at the entry of your last tank reactor. And with this, you can make sure that your concentration of component B is low in every single reactor. So this concept is also applicable for tanks in series. Yes. But what you have to take into account here, again, for simulating, since you are adding here an additional volume flow, only with your component B, your residence time for each vessel is decreasing because you have a higher volume flow through every tank reactor. This is just the case if you say, okay, my CSTR, they all should be the same size. You could easily say, okay, if I know exactly how I want to feed my component B, then you could design your tank reactors in such a way that they all have the same residence time. But this is then detailed design. For if you just want to say, okay, what is a good idea, how can I operate my reactor, then it could be like this. Okay, so what I wanted to show you is if you have a competing parallel reaction. Here it's right now we just look at isothermal conditions. If you have an isothermal reaction with a competing parallel reaction, then what is the procedure? So I would recommend you to determine the ratio of the reaction rates and then identify the effect of low or high concentrations. So normally it's quite easy to see what should be high, what should be low to get a good ratio here. And then it depends on what kind of reactor you want to operate. If you say, okay, I want to have an easy life, I just want batch operation or CSTR, then just start with the surplus of the favorable component. So in our case, it was component A. You start with an excess amount of component A. And if you say, okay, I can also go for a more complex reactor. If you want to do semi-batch or PFR or tank in series, then you can also think of continuous feeding of the component with a negative effect. In our case, it would be component B. And you can additionally, charge a surplus of the favorable component, in our case A. So here you can just play around with the starting amounts of your components, of your educts, and for semi-batch, PFR, tank in series, you can combine both. You can have an excess amount and you can have this continuous feeding strategy. Okay, thank you for your attention and all the best.